Okay, we're going to continue on what we talked about last time. We're getting to chemistry here. We'll be starting something called stoichiometry, a fancy word for quantitative relationships between the reactants. That's kind of the guts of what most people have trouble with in 1A, 2A, 3A. Unit 1 is also a weak point. That's why I spent a lot of time on that. But this unit is particularly important. This is the next unit. Next unit is on solution within the active concentration. Now, we're going to be using very large numbers today. Numbers like the 23-0 after big numbers, and very, very small numbers as well. Like 20 or 30 zeros in front. So big time extremes. So your scientific notation is going to be really important. Also, your EE on your calculator is going to be used frequently. Okay, so as a quick review from last time, we talked about the periodic table. And all periodic tables have a series of boxes, and those have a number of numbers in. One is a symbol of what the element is. And sometimes they'll actually have the full name. Now, the periodic tables we're using will have the name in it. But your next class is up for grabs. Some people use them with names, some people use them without. It just depends on who's teaching the class. Okay, they also have two other numbers. An integer, and that integer is the number of protons. That's also called the atomic number. The other number is a decimal number, and that is the average of all the isotopes of that particular element. So that would be like carbon 12, carbon 14, carbon 13, carbon 11, carbon 15. Notice the bottom number is 6. That does not change. That changes if we're on the carbon. The top number is a combination of protons and neutrons. The number of neutrons can change. It doesn't affect the chemistry. Okay, so we're going to be using this decimal number today a lot. Okay. So what exactly is the decimal number? I said it's the average of all the isotopes. Yeah. What is it? Okay. If we were to take and put this many atoms of carbon on a balance, it would weigh 1201 grams. Now notice that's kind of a big number. Working number. That tells you how small atoms are. For atoms to be this many of them, weigh 12 grams, they've got to be really tiny. And they are very, very tiny. Now, we have a fancy name for that. The guy that discovered that number, 602 times 10 to the 23rd, his name is Avogadro. And guess what the name of the number is Avogadro's number. So frequently you'll hear people say Avogadro's number, blah, 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 blah. And the real useful part of all this, though, is we have a new unit that you might have heard of before. It's based on the word molecule, and it's called mole. So 1 mole of anything is 6.02 times 10 to the 23rd of them. Now that's just a number, conversion factor. We could have 6.02 times 10 to the 23rd ducks. Doesn't matter. It's just that because atoms are so small, we need a big number to represent them. So you're going to use mole for the rest of the semester. Mole this, mole that. Everything is related to mole. You'll hear molar mass. The molar mass of carbon is 12.01 grams per mole. Another conversion factor. And as you remember, the inverse of conversion factor is also true. So molar mass. Another conversion factor. Now that's based on the elements specifically. There's another conversion factor built into that 602 number. So we have 6.02 times 10 to the 23rd atoms or molecules, depending on what we're working with, per mole. And then the inverse is true also. Know those. One of them, it doesn't matter what chemical we're talking about. Just accounting. Like I said earlier, we're talking about ducks, atoms, or molecules. Doesn't matter. This grams per mole is very, very, very specific. The chemical itself. So you've got to know the formula for that chemical before you can calculate its molar mass. So let's look at some examples of molar masses now. It's what I mean is a flaky display. Okay. Here's a periodic table. Now this is a typical one you can get in 1A. Notice carbon, there's no word carbon there. It's just C. You're expected to know that. Now, some of your teachers are going to make you memorize stupid things. I don't believe in memorizing something that you can get on your smartphone in 4 seconds. I'll always give you the periodic table on every single test. You don't have to ever. Now, some of this stuff you'll use a lot. You can use carbon a lot, nitrogen, oxygen, hydrogen. Those you'll probably know, not because you're memorizing, just because you use them a lot. Okay. So what we're going to do is we are going to round everything to 2 decimal places. Okay. And when you're in 1A or 3A, you're not going to round. You're going to use all the decimal. And for me, it defeats the purpose of understanding these numbers. Okay. So we're rounding everything to 2 decimal places. So for example, Carbon's already 12.01. Hydrogen, if you look on here, is going to be 1.008. Okay. All right. So what does a mole of hydrogen weigh? What's a mole of hydrogen atom? 1.01 grams. How many are there? 6.02 times 10 to the 23rd. Of them that weigh 101 grams. Yeah.
So what's special about that number? Why is it 6.02? Why isn't it 7?
I don't know, 250 years ago, Avogadro.
They just decided that was
Yeah, so we've been using it ever since. So.
in terms of, I would have just done 10 or something.
That
That would have been a lot easier.
Yes, we're on one.
Yeah.
1 times 10 to the 23rd. I know. In fact, it goes out about 20 decimal points. It's not exactly 602. I know. That's why I don't like using this thing. I don't know why, actually, I have another pair of cable. I don't know why this one's up here. Jim's, you know. Okay, so getting back to the hydrogen thing. So, if we're gonna put 6.02 times 10 to the 23rd atoms of hydrogen on a scale, it would weigh a little over a gram. So the molar mass of hydrogen is what? 1.01 grams per mole. Now sometimes we use something called molar mass. If we're talking about a molecule, be nice. Atomic mass. We're talking about an atom. Okay, so working with a molecule, it's going to be molar mass. We're working with just an atom. Single atom, like atomic mass. Atomic mass. CH4 would be a molar mass. Okay, so atomic and molar. Atomic is just single atoms. Molar is a molecule. Copper sulfate. Is that an atom or a molecule? Molecule. Okay. If more than one atom, it's a molecule. So what's the molar mass of copper sulfate? Well, we have to go into the periodic table and add up one copper. And copper is 6350. 6355. And how many coppers are there? 1. Okay. So that means there's a 1 there. And most people leave it off. How many sulfurs are there? One, and sulfur is 3206. And oxygen. How many oxygen are there? 4. Okay, 4 times 16 is 64. On what? $32.06. Really? However, this may be a short one. Okay, on tests, the periodic table I give you for the tests is the one everything will be based on. So whatever that one said, use. That's interesting. Normally,
This one also 6, 7.
yeah. It must be about 4 or 5 decimals out. Okay, so let's look up now. Let's add up copper sulfate. What is a molar mass for copper sulfate? Okay, so the molar mass for copper sulfate is 159.61 grams per mole. Now, it depends on what state the copper is in. It could be that version of copper sulfate. In this case, how many sulfurs do we have? Two SO4s. One oxygen, 2 sulfurs, 1 copper. Now, the reason why still 1 copper is parentheses are not around copper, only around the SO4. Okay, so let's look at a typical problem. Now, these are some typical problems you're going to find dealing with moles, molar mass, that kind of stuff. So let's go through these. I mentioned 2 conversion factors, and there's one more you need to know. Where did I write the conversion factor? Oh, right here. Okay, so there's molar mass, and that's specific for the chemical. Avogadro's number is not specific. It's for anything. And there's one more if we're dealing with gases. Gases are really weird because they're compressible, easily compressible. So we're going to deal with volume on gas. we also weigh something. When we're talking about a mole, there's 22.4 liters in 1 mole for any gas. Doesn't matter if it's H2 or UF6. 22.4 liters per mole on the inverse, and that's at standard temperature pressure only. 1 atmosphere, 0 degrees Celsius, standard temperature and pressure. Anything else, it's not 22.4. Now you're going to be getting into something, using something called the ideal gas law to figure out what it is if it's 2 atmospheres and 12 degrees. It's a simple formula. Okay, but most of the time in here we're working with standard temperature pressure SUP conditions, 22.4. We have 3 conversion factors. Our gases only 22.4 liters per mole. 6.02 cents in at the 23rd atoms or molecules per mole, and then grams per mole depending on the chemical. Okay, so let's practice some problems here. Standard temperature pressure. Okay, so how many moles are in 2.34 grams of water? Okay, we're back to unit 1 kind of stuff. What's given? 254 grams of water on the left. What are we trying to calculate? Mole goes on the right, and we have a conversion factor to get there. Okay. So the conversion factor that has both grams and moles in it is the molar mass. So we want to cancel the given. And what's the chemical? H2O. So 2 H's and 1 O. Okay. H's are 101 apiece. And oxygen is 16. Okay, so that's 1802 grams per mole. Okay, grams cancel, leaves us moles. Trying to calculate moles. Now you're going to find in this class that a lot of things are related back to mole. Mole. That's frequently an intermediate step to be taken. So I've been saying, if in doubt, convert to mole. You'll usually be in good shape. Because everything relates back to mole. Okay, so okay, how many sig figs is the answer? 3. Now this is straight out of unit 1. Given, we're trying to calculate conversion factors. We're just using the chemistry conversion factors now. And kind of the inverse of that problem. Then we're using the 1802 for water. And well, that's about as simple. Frequently, two-step problem. The intermediate seconds to molar. Okay, so let's look at. Okay, so we have 2.34 grams of water. And we want to go to liters, gaseous liters. What are we going to do? What do we work on that when we start? We're putting moles and grams, right? And it'll get us to moles. Yes, exactly. Okay, so if in doubt, convert to moles. So we're going to go grams to moles. And it's 1802 for water. That gets us moles. Now we can use the 22.4. There, everything cancels except for liters. We're looking at 3 sig figs. That would be 2.91 liters of gaseous water. Basically, that's. Okay, so again, we're using that intermediate moles then. It'll be your front. Okay, does that problem make sense? Okay. Okay, how many molecules of water? Whenever you see how many, that's counting. I want you to think of Avogadro's number. How many? 602 times 10 to the 23rd. Okay. So we're starting with gaseous water at STP. Okay. We want to go to molecules. So what's going to be our intermediate step again? Moles. Moles. We're going liters to moles. That's 22.4. Now we're going to go from moles to number of molecules. Okay. 3 sig figs is the answer. Oh, goody, this doesn't have an EE. So lots of molecules. Use them a lot. Now to the end of the semester. Okay, now this is an interesting problem, seemingly very simple. Okay, given is 345 liters of water at STP. How many atoms? And what's the difference between an atom and a molecule? Exactly. Molecules are made up of atoms. Perfect. So here we're asking about individual inches. Well, we can get to moles. And we can get to molecules of water. Unless I said molecules of water. Now, is that the same as atoms? What does this calculation give us? Molecule. Now, as a little aside, if I have 10 bicycles, how many wheels do I have? 20. How did we reach that? Well, 5 by 2 because there are 2 wheels per bicycle. Okay. Now let's go to water. H2O. How many H's are in a molecule of water? 2. We have a new conversion factor. Because right now we're at molecules, not atoms. We have to put one more conversion factor in. 2 H atoms for 1 molecule. Okay, does that make sense? Why we needed that last step? Because our units won't come out unless we have that last step there. Okay, so that's what we got here. Okay, why isn't it one sig fig? Why is it three sig? It's three. How many is that? Infinite. It's exactly 2 to 1. Not 2.01. Exactly 2. Exactly. That means it's infinite. So we don't count sig figs there. And 3 sig figs.
Okay, you're saying the middle one's not infinite?
Hmm?
The middle one, we do not see things. The 6.92.
That's right.
Yeah,
3 sig figs.
it's not infinite, it's not a.
That's infinite. That's 3 sig figs.
Conversion.
That's infinite, but not that. The 602, but it's not infinite. It's in a multiplying range. If you multiply infinite times 3 sig figs, your answer is fig.
But that one's infinite.
It's just infinite because it's exactly 2. And then this side is 22.4 is approximately. That's 3. Hello? Yeah.
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 And then you say.
All the units cancel except for atoms. So moles cancel, molecules cancel, we're left with atoms. Of what? H's. Stands for hydrogen. Like in water. H2O. 2 hydrogens to 1 oxygen.
Right. 6.02 multiplying 10 and 3 molecules or it's atoms. And how do you guys get 2 H atoms? Like which one?
Which likes molecule versus atom? Okay. It's because this is for the gas. And the gas in this case is water. H2O. That's why we convert the molecular thing.
Yes, I understand that, but why there is a 2 H atoms and 1 molecule?
Yeah.
This is like we have.
1 bicycle, 2 wheels. You have 2 wheels for 1 bicycle.
Okay.
2 atoms for 1 molecule of water.
Oh, only 1.
Yeah.
Okay. So just the hydrogen, it's gonna be.
Hmm?
So just hydrogen, it's gonna be the atoms and molecules, the same thing, not 2 hydrogens.
You take H2 apart. So we have 1 water. How many oxygens do we have to take it apart?
Oxygen.
1.
Mhm.
2 hydrogens. Right? That's why this is required. Because otherwise, it's simple.
1 molecule of water, now I understand.
Ever?
Yes.
Okay. Yeah.
One or both, you know?
Oh, yeah. Hot.
Lights,
What?
are the lights working? Are the lights still lit? Can you turn them on?
Would you like me to turn? Let's open this one. The problem is always a battle between how bright the screen is versus the brightness of the light. You still see okay?
That's okay.
It doesn't matter to me either way. Okay. So this is a pretty good spot in terms of stoichiometry problem. Stoichiometry is going to involve a reaction. Now, up until this point, has anything reacted? No. Nothing has reacted. So the next question is, well, what does something react? Does that affect the calculation? Let me give you an example problem with that. With the combustion of methane to carbon dioxide and water, how many grams of water produced of 15 grams of methane are consumed? Is there a reaction going on here? Yes. We have to take a different perspective on how we do this calculation. And this is stoichiometry. A very simple example is stoichiometry. And we have a reaction going on there. Up to this point, you've just this kind of rename thing. Nothing's happening for them. For water, they say water. Now, so what we're going to do is I want to talk about a reaction. Now, a reaction is taking something and changing it. Fancy name for what we start with is called reactant. Fancy name for what we end up is called product. So we have to look at this paragraph and figure out what are the reactants. Well, it says with the combustion of CH4. CH4 is methane. That's typically what comes out of your natural gas outlet. Methane. Okay, and then we burn it. Whenever you combust something, you convert it. You can convert the carbon from the oxide, convert the hydrogen to water. And that's called oxidation. So we're oxidizing the reactant. Okay, so we oxidize the C, the CO2, we oxidize the H, the water. Now, in Chem 1A, possibly 2A, for sure 3A, you're going to have to know what that means. Okay, and here I'll always give you the reaction itself, as opposed to a paragraph of words for you to figure out. Okay, so the reactants in this case is methane, and the products, plural, are CO2 plus water. Now, as an exercise tomorrow morning, I want all of you to start your car and run around the back and tell me what's dripping out of your tailpipe. Does anyone know what that is before they go in front? You ever wondered what's dripping out of your tailpipe? Wait 10 minutes, nothing's dripping out of the tailpipe. Water. So your engine's producing water and carbon dioxide. Have you ever wondered, seen a jet up in the sky? What's coming out of the back of that jet?
But also. It's like air.
That white stuff called a contrail, CON, and it's ice crystal. Because they're very, very small, that's why they float. And so, jet fuel is mainly C8H18 octane. Jet fuel, JP4 is oxygen for. So when you burn octane, you also produce carbon dioxide and water. For jets, military jets, this is a problem, the contrail. Because you can see those from way up. So World War II, in the latter part of World War II, there were Allied bombings of like 1,200 B-17s in the sky in some of these cities that were bombed. B-17 has 4 engines. That's 4 contrails per plane times 1,200. That's 4,800 contrails. Do you think the Germans knew they were coming? Can't hide it. Problem. Unless you fly really low or have some special device in your exhaust, turn the water and something other than ice. The problem is planes fly really high. On the top of mountains, way out. You have ice because it's cold up there. And very increasing altitude, it gets colder and colder and colder. So if you're producing water, it turns to ice. No problem. Okay, what's the difference between these two? Hydrogens are here. 4. How many hydrogens are here? 2. So what's wrong with that? Yeah, you're not, otherwise we have a big explosion. Big explosion. Notice no explosion. What about here? How many carbons do we have here? 8. 1. Problem. So the thing with chemical reactions, you just can't write it. You have to balance them. Balancing means that we have 8 carbons here, we have to have 8 carbons there. We have 18 hydrogens here, we have to have 18 hydrogens there. But tomorrow, we're going to spend the whole time on balancing equations. Actually, there are 2 ways to balance equations. One is very complex, and the other is called guess and check. Guess which one we're going to use. Guess and check. Okay. So when this is the essence, first thing you do, you're going to have a problem with the chemical reaction. Now, there's something very important missing here. Can we burn anything in the absence of oxygen? So we need to have oxygen there as well. Now we have carbons, hydrogen, oxygen on the left. Carbon, hydrogen, oxygen on the right. These aren't equal. I'm going to show you a technique to make them.
Equal because we have two oxygens here and one oxygen.
So we do the valve. And yeah, tomorrow. We're gonna focus on totally balancing equation. I'm gonna give you lots of practice. Sometimes it's trivial, other times. Okay, so, what time? Rules one, why don't you come up and get your tests? When you look at your test, make sure I subtracted correctly. If you think your problem is correct and I marked it wrong, talk to me. I love getting 20 factors to it. We have a wet lab today, so hopefully all your pre-labs are done.